Dear friends, today we will discuss applications of Gauss law and continuous distribution of charges. Let's first start from continuous distribution of charges. So till today our discussion was only about point charge. I have told you from the starting class what is point charge. The dimension of the charge is negligible in comparison to distance. We have discussed only point charge and also about 2 point charges separated by finite distance and dipole. Means all discussions till today was about only point charge. But now we discuss when many number of charges will reside on a surface or somewhere else, then how they can distribute. Many number of charges, infinite number of charges, how they can be arranged? They can be arranged in 3 ways. One, they can arrange in 1 dimension, they can arrange in 2 dimension, they can arrange in 3 dimension. So let's now discuss. So they can be arranged in 3 types. First you see 1 dimension arrangement, or that is called line charge. Line charge means charges present on a line. See here, charges present on a line. A simply long, very long charged rod can be treated as a line charge. When many number of charges are present, then total number of charge doesn't matter. Infinite number of charges are present. This line extends to infinite. Then you see total amount of charge doesn't matter. In that case, what we'll see? We'll find charge density. Charge density. Density, what you have read in lower classes as well as in class 11th. What is density? What if I ask you what is density? Immediately from your side answer will come. Density is mass by volume. No, dear students, that density is mass density. Now don't confine the density word to mass only. Remember, density of mass, density of charge also can be. Density of many things, density of lines of force also it can be. So what density you have read, that is only mass density. Mass can be distributed in how many ways? 3 ways. In a line or a long wire. In a line, mass can be distributed in a plane, a sheet of paper, 1 page of your copy. Mass can be distributed in a volume, for example your cricket ball. So mass can be distributed in 3 ways. You have defined mass density also in 3 ways. Density is mass by volume is not only the formula of density. That is the density formula when the mass is distributed in a volume, means in 3 dimension. When mass distributed in a line, that is called linear mass density. I am just telling you linear mass density lambda, that is mass by length. When density distributed on a surface plane sheet, that is sigma. So that is mass by surface area. When density mass distributed in a volume, that is rho. Rho is the volume mass density. Which quantity earlier you had told on density, actually that is volume mass density. Okay, so this is mass by volume. Mass density is of 3 types: lambda, sigma, rho. Similarly, charge also has 3 density. Now we have started linear charge density. Similarly to that, we will now find the density is important here. To find this, what we will do? We will consider a small length L. Within that length L, how much charge is present? Suppose Q charge is present from this to this length L. Then what quantity will define? Linear charge density. Charge by length. Charge by length, the same symbol as linear mass density. Charge by length. If this distribution is not uniform, suppose Here the density is different, here the density is different, here the density is not uniform. What will do? In those cases, what will do? We will take lambda as dq by dl. This is another formula of density. If we consider a small section, just q becomes small, dq, l becomes small, dl. So this is linear charge density when in a long charged rod. And what is the unit? Coulomb per meter is the unit and dimensional formula. I will not do all. I left for you. You will find it's a dimensional formula. This is about linear charge density or linear distribution of charge. Now we come to two dimension, means surface distribution of charge. How the charge will distribute on a surface? You see, this is a charge sheet, plain sheet of charge, or this is a cell, spherical cell. This is cell, remember, inside is a hollow. Cell means inside is a hollow, spherical cell. Here charges remain on the surface of the cell. On the surface of the cell. Is it clear? So here it is surface distribution of charge, means two dimension. So we write surface distribution of charge is sigma is q by s. Sigma is q by s. On surface charges are distributed. Charge divided by surface area, or in small you can write dq by ds. Accordingly, SI unit coulomb per meter square. Dimensional formula you will find. Okay. Then come to volume charge distribution. Volume charge distribution, charges present in a suppose non-conducting solid sphere. Non-conducting solid sphere, you see. I told you non-conducting solid sphere. Here I told you cell. Suppose I will take one conducting solid sphere, what will happen? Also charges remain on the surface. This is conducting solid sphere. Conducting solid sphere is same as a spherical cell. Same as spherical cell. You may ask the question, inside it materials are there. Inside it, suppose it is iron, made up of iron ball. Inside it iron is there. But still why charges are not there inside iron? We will discuss about that in the next chapter. But remember, inside conductor there is no electric field, no lines of forces pass, and no charge is there inside the conductor. So conducting solid sphere is equivalent to spherical cell. But this, for that I told you, non-conducting means charges present in the volume as well as on the surface. Three-dimensional distribution of charge. So here the density is volume charge density, just like your volume mass density, rho. Rho is equal to q by v or dq by dv. Is it now clear about the continuous distribution of charges, how charges can be distributed in line, surface, volume? My question is here, when you have taken point charge to find electric field intensity, what you have done? You have used simply Coulomb's law. Simply Coulomb's law you will apply. It's okay. Or between two charges you can find the force using Coulomb's law. But when these type of cases comes, then what will do? We cannot use Coulomb's law because Coulomb's law is only valid for point charge. How can we find electric field intensity, electric field strength due to this continuous distribution of charges? Not using Coulomb's law. What we can do by using Gauss law. Okay, but we can do these cases, some cases of line charge or some semicircular arc, one ring, due to one charge ring, we can do by using Coulomb's law, but we have to adopt integration method. Those things I will do in my next lectures. But now you see, Gauss, by using Gauss law we can solve very easily in a shortcut way. But if we use Coulomb's law, then we have to adopt integration method. It will be very lengthy. So by using Gauss law, see how easily we can able to solve. That means now I am coming to applications of Gauss law. Gauss law, in your book you will find three applications. line charge, surface charge, then spherical shell, conducting spherical shell. But I'll do today 4 applications of Gauss law. You see, so first you come to linear charge, infinite line charge. Line charge, this is infinite line charge. Now you take infinite line charge. This is one infinite line charge. It's extend up to infinite by dotted symbol is shown. We will find intensity here at point P, which is at a distance R. P is any point at a distance R from infinite line charge. Lambda is equal to linear charge density, means Q by L. Q by L, lambda is linear charge density. P is any point at a distance R. So first what we have to do here? We will use Gauss law. To apply Gauss law, what we need? We need one Gaussian surface. We have to draw one Gaussian surface, and I have told you Gaussian surface you will do according to your comfort zone. How easily you will get the answer. So I am taking the Gaussian surface one cylinder. You see same R here. I am taking the Gaussian surface one cylinder such that point P lies on the Gaussian surface and it encloses L length of the rod. Rod extends up to infinite, but I consider L length of the rod which is enclosed within the Gaussian surface. So we will find now intensity due to this length. You may ask the question, what about the infinite length? What about this? They have the contribution here also, but their contribution is neglected. So I took now L length of the rod here enclosed within the Gaussian. How much charge contribute to intensity there? You have to enclose them by Gaussian surface. Now see, this is our Gaussian cylindrical Gaussian surface you consider. So using Gauss law, phi equal to Q in by epsilon naught. What is phi? E vector dot ds vector Q in by epsilon naught. This one I have told you to give this close symbol only when you use Gauss law. Then this is surface integration. Then you see I am going to do the integration over the surface of the cylinder. But cylinder has how many surfaces here? 3 surfaces. 2 plane surfaces, 1 curved surface. It's better if you split the surfaces into total surface into 3 surfaces. Let's now split. This surface you take S1 vector. This one I am taking S2 vector. This surface you take as S3 vector. Okay, now you do the integration, split the integration into S1 E dot ds, S2 E dot ds, then S3 E dot ds, Q in by epsilon naught. So you now see for S1, while the direction of electric field is positive, this is the direction of electric field intensity. From positive, it is away electric intensity direction. So now you see for S1 vector is here, electric field is here. What is the angle between electric field and S1? It's 90 degree. So this is E ds cos 90. This is E ds cos. Again for S2 same thing happens. Angle is 90 degree. Again plus S3, it is E ds cos. Same direction, so 0 Q in by epsilon naught. Now you see, I am not giving the close symbol here. Here was the close, but here no close because I split the closed surface into 3 surfaces. So no, you will not give any close symbol here. So this is now 0, this is now 0 cancel, and this electric field is constant on the Gaussian surface, same distance. So integration of only ds Q in by epsilon naught. Now what is the integration of ds? Ds integration is, it is done only on the curved surface area of the cylinder. What is the curved surface area formula of the cylinder? 2 pi r L. curved surface area of the cylinder. Q in by epsilon naught. E, so Q in 2 pi RL epsilon naught. What is Q in by L? I had told you just before, this is lambda by 2 pi epsilon naught R. So this is the electric field formula due to infinite line charge at a distance R. Is it clear? Now I think you understand. But in exam, what questions will come, what attached questions will come here? The questions will come, how E depends on R and draw the graph. Very easy. Always this graph comes in exam. E versus R. You see this is the graph. E depends linearly with R. Inverse proportional with R. Okay. So next question will come. Write its vector form. How will write its vector form? E vector is equal to lambda by 2 pi epsilon naught R into R cap. This is the vector form. What is the direction of R cap? It is away if charge positive, radially away if charge is positive, and radially towards if charge is negative. So this is about infinite line charge. Now we will go to application number 2. Let's come to application number 2. Infinite plane sheet. Infinite. This is again infinite plane sheet, and that is thin plane sheet. Means its width is neglected in comparison to the size of the sheet. Infinite plane sheet. Now let's consider one plane sheet. This is plane sheet. It has many charges on it. It extends up to infinite. It's a plane sheet now. See, many charges are there. We will find the intensity at a distance R at point P. Similarly, we will consider surface charge density. Sigma is equal to surface charge density here. Let's consider one surface area, S surface here. Within that, how much charges present? You just count. Suppose Q charges, then by S. This is called surface charge density. We will find intensity P at any point at a distance R. What will do? You have to consider one Gaussian surface, so that these charges will enclose inside it also. The charges which contribute electric field, they must be enclosed within it, and these charges contribution are negligible as an infinite sheet. So for them, which type of Gaussian surface I am drawing? So I decide to draw one Gaussian surface like this. This is point P, Gaussian surface like this. This is a cylindrical Gaussian surface. Is it now clear? This Gaussian surface, is it okay? No, it is not okay. Why it is not okay? Now the question is coming to your mind. Why it is not okay? Because the charges which contribute the intensity at point P, they are not enclosed by the cylinder. Rather, they present on the surface of the cylinder and on the plane surface of this part of the cylinder. You know, charges present on the surface are not taken into account. They will not be considered in Gauss law. So what I have to do? I extend this cylinder now again in the backward direction, in the back of the set. Means cylinder is extended from this to this. R distance to this side, R distance to this side. Now we extend the cylinder like this. Now is it clear? So this area of a cross section is S. Cylinder extend to back side. Now these charges are enclosed within the cylinder. It has three surfaces. Let us take this one as S2, this one as S1. These are the aerial vectors, and the curved surface is S3. I split the surface into how many surfaces? Three surfaces, S1, S2, S3. And as this is positive charge, electric field here will be in this direction, and electric field here will be in this direction. This side electric field I cap, and back side electric field minus I cap. Okay. Now we will go to using Gauss law. Phi equal to Q in by epsilon naught. Phi is E dot ds Q in by epsilon naught. It splits into three surfaces, S1, then S2, then S3. E dot ds. No close sign here, no close sign because it splits the surface, close surface. So now for S1, what is the angle you see? S1 and electric field both in the same direction. So E ds cos 0, S2, E ds cos, see S2 and electric field 0, then S3, E ds cos S3 this side, electric field this side. Angle is 90. Q in by epsilon naught. So this one electric field constant on the Gaussian surface taken to outside, ds integration is S. Then electric field constant taken to outside, ds integration is S. And this is 0 as cos 90. So Q in by epsilon naught. What it comes? 2E is Q in by epsilon naught. Then what is E? Here I am going to see E is equal to Q in by 2S epsilon naught. But Q in by S, this is a sigma. So sigma by 2 epsilon naught. This is the electric field. Due to infinite thin plane sheet. What questions will come from here? Same question. How electric field depends on distance. Now you see, does the electric field depend on distance? No distance expression here. Means electric field is constant. If sigma is constant, everywhere uniformly charged, then also electric field is constant here. So it doesn't depend on distance. If it doesn't depend on distance, now we can draw the graph. How with the graph? If it doesn't depend on distance, electric field is constant. Always comes in exam with this question, this graph. Then next one is question will come, that is a vector form. E vector equal to sigma by 2 epsilon naught n cap. Always it comes and write the vector form. Where is the direction of n cap? N cap direction is, if positive then away, if negative then towards. So this is about infinite thin sheet of charge. Now we come to the application number 3. But before that I am telling you one thing. This is about infinite thin sheet. But if a thick sheet will come, what is thick sheet? You see, this is one sheet. If this is made thick, the sheet is now thick sheet. Means here also charges present. Charges present here. Also charges present at its back. When you find this expression for thick sheet, expression will be different. It's thin. I am discussing now thick. How expression will be different? You see here point is P. E point P is here. What happened? Here is due to this side electric field will come. Also due to the back side electric field will come. Due to this side, this is the direction of electric field. Even due to this side. Due to this side electric field is in this direction. Due to back side, when you consider the back side at this point, as that is positive, also electric field will be away. Also electric field will be away. Just I am giving you one situation here. You see this is the thick sheet. You consider this is one side and this is one side. Charges present this side, charges present this side. I will find electric field at this point. Now see, at this point I will find electric field. When I find electric field at this point, what will happen? So due to this side, electric field will be away. This side, see. When I will find electric field due to this side now see. I will find electric field due to this side. What will happen? When this side will give electric field, you just neglect this part. Because it provides its independent electric field. When it provides electric field, it has no role. So this side you neglect. So now it is charged. So when it is charged, its electric field here will be where? also away because it is positive. It is positively charged. So here electric field also will be away. If we consider this side also will be away. Here also will be away. That means due to this part electric field is away. Also due to this part electric field is away because it is positive. In same direction. If it's away, then what is the total electric field? So E1 vector plus E2 vector. But both are same, sigma by 2 epsilon naught I cap, sigma by 2 epsilon naught I cap. It is coming sigma by epsilon naught I cap. So this is about the electric field. If thick sheet come. Now you remember, when thin sheet electric field is sigma by 2 epsilon naught. But when thick sheet come, electric field is sigma by epsilon naught. You mark this different, don't confuse in your book. Somewhere it is written sigma by 2 epsilon naught, somewhere it is written sigma by epsilon naught. When only epsilon naught thick sheet, when 2 epsilon naught that is thin sheet. Now I will come to the third application. Third application now will come to third application. What is the third application? Spherical cell. Now you consider one spherical cell. This is a spherical cell. Of radius you take r. It's a spherical cell. Due to spherical cell we will find electric field. It's a 5 mass derivation. First line charge is 3 mass derivation. Plane sheet, infinite plane sheet is 3 mass derivation. And this is a 5 mark derivation. It has 3 cases for which it is 5 mark. But you have to write charges present on the surface. I have told you because it's spherical cell, nothing is inside. Spherical cell is also same as this is spherical cell. Spherical cell also same as conducting solid sphere. Same thing happens, conducting solid sphere, because I told you in conducting solid sphere charges reside on the surface. Okay. So R is the radius of the spherical cell. Charges remain on the surface, so which density will come? Surface charge density or volume charge density? Obviously surface charge density. Sigma charge divided by 4 pi r square surface area of the sphere, because charges remain on the surface. So charge divided by 4 pi r square. Now we come to find electric field intensity in 3 cases: inside, on, then outside. Consider a point P. Inside first we will do case 1. I am doing inside, small r less than capital R. I consider a point P at a distance small r. Small r is less than capital R, so point is inside. Now we have to draw one Gaussian surface. Which type of Gaussian surface we will draw? Obviously we will draw one spherical Gaussian surface, symmetric to it. Spherical Gaussian surface. So using Gauss law, phi equal to q in by epsilon naught. But what is phi? E dot ds q in by epsilon naught. But what is the q in here? Q in is 0. No charges present within the Gaussian surface. If no charges present, then what is the electric field? Nothing to do, it is 0. Electric field inside a spherical cell is 0. Same thing as well as inside conducting solid sphere is 0. No charges present inside it. Now come to case 2. Case 2. Case 2 will do outside the Gaussian surface. We will come to outside point. Consider a point P outside now. I am drawing another figure for that. Outside now we will go to one point outside the Gaussian surface. Let's take one point P here. Draw Gaussian surface. This is the Gaussian surface. At a distance smaller. When outside, then R is greater than capital R. Again use Gauss law. Phi is q in by epsilon naught. But what is phi? E dot ds, then q in by epsilon naught. E dot ds. But everywhere on the Gaussian surface you will see, everywhere you see, here you see, consider small elementary vector. This is the ds vector along the radius. and also electric field will be in that direction. Both electric field and aerial vector will be in the same direction. This is sphere, so electric field also will be radially outward. So here ds vector is also radially outward. For the angle between them, EDS cos 0. Everywhere angle is 0, and charge enclosed is whole charge is enclosed inside it. So this is Q. Now come do the integration. What will get? E. For the integration of ds, E is constant. I have taken to outside. For the integration of ds, 4 pi r square. But which r? Capital R square or small r square? This is the confusion of some students, those who never understand. This is small r square. Always remember, the integration is always done on the Gaussian surface. So it is small r square. Q in by epsilon naught. So E is equal to Q in by 4 pi r square epsilon naught. So what expression you got here? You got the expression E is equal to finally 1 by 4 pi epsilon naught Q by r square. Is it clear? So this is the expression when you consider a point outside the Gaussian surface. But one thing I am telling to you, have you seen this expression earlier? Anywhere have you seen this expression? Yes, where we have seen? This is the expression of intensity due to point charge. K Q by r square 1 by 4 pi epsilon Q by r square. That means the expression of intensity due to point charge is same as the expression of intensity due to spherical shell. Yes, both are same. It is coming same. If it is coming same, suppose something is here. I just hide one, something is here inside it. I just hide. I will find the intensity at this point P, which is at a distance R. I will tell intensity here is 1 by 4 pi epsilon naught Q by r square. So what is here at this point? What is here? What I hide here? Is there any point charge inside? Maybe, because expression is coming like that. Is there any spherical shell inside? Maybe, because expression is coming like that. Means point charge and spherical shell both behave same way. Yes. So what you will write here? You will write this expression is similar to the expression of point charge. So the charges resides on the surface of the spherical shell behave as if they are present at the center. When you consider the point outside the spherical shell, remember, when you consider the point outside the spherical shell, charges resides on the surface of the spherical shell behave as if they are present at the center. In exam, the question will come. Charges present on the spherical shell resides on the surface of the spherical shell behave as if they are present at the center. Prove it. Prove it. Then you have to do this once. Only one case, outside case you do, and you get this expression. Then you write as expression is same, like point charge. So the charges resides on the surface of the spherical shell behave like point charge, behave as if they are present at the center. Now the conclusion is drawn here. Charges present on the or resides on the surface of the spherical shell behave as if they are concentrated at the center. Now come to on the surface. If you come to on the surface, case 3, nothing to do here. You can do in the same way I am doing this one. If when case 3 comes, I am making it case 3, all of you see, R is equal to R. Then you will do, then it's no problem. But here on the surface means now this is not your Gaussian surface. This is your Gaussian surface. The surface itself is the Gaussian surface. Then you match the question. If the surface of the spherical shell itself is Gaussian surface, means charges present on the surface. How we will take them? How the charges enclosed within it will be Q. Now the question may come to your mind. If the surface, when you consider on the surface, R is equal to R, then the surface itself is Gaussian surface. Means charges present on the surface. If on the surface, how they are considered, how they are taken into account? This should not be taken into account. How they are taken into account? Okay, I am telling you, when in this case come and you consider Gaussian surface, you have to take the Gaussian surface just above the surface of the conductor. Just above the surface of the conductor, you have to take the Gaussian surface. R plus dr. Radius is R plus dr. Very small, little small increase of radius you have to take at that time. Okay, so now this is capital R. R plus dr is negligible. So 4 pi r squared become now, and this is r square. But when this r square come, you see this q in by 4 pi r square, it is nothing but sigma. So it is sigma by epsilon naught. I understand electric field is sigma by epsilon naught. Okay, so now let us draw the graph. Always it comes in exam to draw the graph, electric field versus R. This graph comes as a 1 mark question. Figure is 1 mark and 3 cases 3 mark. Totally it's a 5 marks long question. Very important. Always comes in exam. Many times it come in the previous years. So the graph, let us now do r is equal to r. At one place r is equal to r, we will start from the center. This is the origin, means this is the center of the spherical shell. From the center when we will come, we will reach our capital R. Small r increase and it become capital R. I have taken this point. So this is small r is equal to capital R, means from these two left side you are inside the sphere, these two right side you are outside the sphere. Now see, when you are inside the sphere, what is the electric field? It is 0. It is 0 means no graph. Graph will be this line. Make this line thick. When r is equal to r, it is sigma by epsilon naught. This is maximum. This is maximum, means immediately we reach at maximum. So from this is by join by dotted line, because this is not the graph. So just join by dotted line. This is the end of the graph, and again graph start from here. When you go to outside point, how E depends on R? Just like point charge I told you, E inverse proportional to R square. So graph will be like this. So this is about the intensity versus R graph for spherical shell. It's a very important 5 marks question. I am going to application number 4. That is, application number 4 is non-conducting solid sphere. Non-conducting solid sphere. This is non-conducting, means charges present everywhere inside it. Everywhere inside it charges present. Radius is capital R. Take the radius capital R, and it is non-conducting, charges present everywhere, means volume distribution of charge. So we will take rho, volume distribution of charge, to total charge by volume 4 by 3 pi r cube. First we will go to case 1. Case 1 is inside, means small r less than capital R. Consider small r. Now draw the Gaussian surface. This is the Gaussian surface. Now I draw here. This is the Gaussian surface. Charges present inside it we will consider using Gauss law. Phi is q in by epsilon naught. Then phi is E dot ds. But what is the value of q in? The whole charge is q, but how much is present there? By unitary method you can find it. By unitary method, 4 by 3 pi r cube volume contain q charge. And this is 4 by 3 pi small r cube volume contains how much charge? Q by 4 by 3 pi capital R cube into 4 by 3 pi small r cube. This much charge it contains. This is q in. This is q in. So 4 by 3 r, 4 by 3 pi, 4 by 3 pi cancel. Q r cube by r cube. So this is q in inside it. So you have to put q r cube by r cube. Then epsilon naught is there. And this angle is 0 and intensity is taken to outside. So this is 4 pi small r square integration, because integration is done over Gaussian surface. Q by R square epsilon naught. So E is equal to R cube R square, it cancel. So 1 R remain here, then 4 pi capital R cube, this is R cube, then epsilon naught. We can again simplify this expression. How? We can place this Q here. What is this Q? Rho into 4 by 3 pi capital R cube. Q. Rho into 4 by 3 pi capital R cube into small r into 4 pi R cube epsilon naught. If you see R cube cancel, pi 4 cancel. How much it is coming? You see how much it is coming now? It is coming intensity rho smaller divided by 3 epsilon naught. This is the intensity inside the non-conducting solid sphere. How intensity depends on R? Directly proportional to R. Inside intensity is directly proportional to R when you are inside. Okay. Now we come on the surface. When you come on the surface, simply you can write E is equal to rho capital R divided by 3 epsilon naught. In this expression, in the small r place, we can put capital R, direct expression. This is on the surface. Is it clear? And this is maximum. But when we come outside the surface, it is same as spherical shell. When you come to outside, you will choose one point P, additions are, draw Gaussian surface, use Gauss law, E dot ds, Q by epsilon naught, Q, here all charges are enclosed. So this is, you know, angle is cos 0, E come to outside, integration of ds is 4 pi R square, Q by epsilon naught, then E is 1 by 4 pi epsilon naught, Q by R square. Expression is same as the expression like spherical shell. So if you draw the graph for this, what will happen? Here one thing also, this is also similar to the expression of point charge. So we can say the charges present distributed in the non-conducting solid sphere behave as if they are concentrated at the center when you consider the point outside the solid sphere. Now you come to the graph. How will draw the graph here? E, R, take a point R is equal to R, which is from the surface, then this side is inside, this side is outside. So inside, how it depends on R? Directly proportional. So it is inside directly proportional. And just at this point, it is maximum. Maximum means what is the value? Rho. What is the value? Value is rho capital R. Just I erase it by 3 epsilon naught. On the surface I have written just before. Then outside the surface it is inversely proportional. So this is about non-conducting solid sphere. So today I completed what is continuous distribution of charge and 4 applications of Gauss law. But one good news for you, that's the 4th application what I did, non-conducting solid sphere, is not in CBSE syllabus, not in CBSE board syllabus. So it may not come in your board examinations. Those who think it as most difficult, you can leave for the exam without any problem. Thank you.